Hi everyone, I'm the coordinator of the METASAT Horizon Europe project, and in this talk I would like to talk a bit about the architecture we have and the final demonstrator of the project. So METASAT was a 2-year project funded by the European Commission. It finished in December, and last month we had our final review. We have we were 5 partners in the project. BSC, we were the coordinators. We provided the hardware and the system software, as well as the high performance use cases. We had Fentis that provided the space qualified hypervisor we used in the project. Ikerland provided support for the model based design. Collins Aerospace provided support on the virtual twin, and OHB provided the high criticality use cases and performed the integration and the demo that I'm going to show you. So we were focusing on TRL or low TRL 3 to 4, so demonstration in a lab environment of novel technologies. So the idea of the project was that nowadays we need higher and higher levels of performance in future space systems that cannot be provided by existing space processors. So the type of functionalities we need are, of course, artificial intelligence. We need higher autonomy. We need to process high resolution data. And most importantly, we want to do this on board. We don't want to send the data back to Earth. These type of functionalities require more complex hardware and software compared to what we currently deploy in space. In particular, we need complex multi-cores, GPUs, and AI accelerators. And on the software side, also, we need more complex, we need truly parallel CPU and GPU programming. In institutional missions, usually we rely on space-grade CPUs and FPGAs. And usually we have a lot of subsystems, and each of the subsystems use different hardware and different software with different criticality, sometimes bare metal, sometimes with a real-time operating system like Artems. So the vision we have in METASAT is, instead of using a lot of different hardware, just to consolidate them in a complex, highly capable processor SoC, similar to the concept of integrated modular avionics that we have in the commercial aviation. This way, we can achieve a reduction of the hardware cost, and at the same time, by integrating everything together, but maintaining time and space partitioning, we don't need to increase the qualification level. So we can keep also the software cost down. And we were also relying on model-based design in our project to manage this complexity. The problem was that there was no such a complex platform that we could use in order to demonstrate our proposals. So we created our own platform with these features based on the RISC-V. So here you can see how it looks like. We have a multi-core based on Noel 5. We have integrated it with the Sparrow AI acceleration unit. This is a short vector unit particularly designed for AI acceleration. And we have integrated that with a Vortex GPU, which is compliant with RISC-V. We have used several use cases in order to demonstrate our project concept. And those use cases have different processing requirements and different acceleration requirements, as well as different criticalities. And we achieved to integrate everything together and demonstrate it on the same single platform. We used 3 use cases. The first one was provided by OHB and DLR. Implemented interlocking. So this is functionality that is traditionally implemented in hardware to protect from wrong software behavior. But a novel thing we have done in our project was to implement this in software, and this way achieving lower qualification cost. We have also had an instrument control software. We implemented AI-based FDIR, fault detection and isolation and recovery. And we have used that for that data from a real satellite, the NMAP from DLR and OHB. In addition to this traditional use case, we had also 2 advanced use cases similar to the previous presentation that we have seen. that was provided by BSc and was based on the open source benchmarking suite that we have created a couple of years ago in a niche activity, which is called OBP MarkML. These are applications for AI that could be used in space in the future. The first one is cloud screening. It's very similar to the previous presentation we have seen, but it detects clouds on satellite images, and ship detection, which detects vessels on satellite images again. And those are accelerated by our accelerator, the AI accelerator, Sparrow, and GPU. Here you can see an overview of our platform. As I said, we have the multi-core with this AI acceleration unit. Actually, we have done the necessary steps in order to increase the technology transfer of this to Geisler. We have a fully qualifiable software stack. It's based on the hypervisor from Fentis. It's space qualified. We can run RTEMs and fully parallel workloads like OpenMP. We have time and space partitioning. We have AI frameworks like TensorFlow Micro, and for the GPU we support also OpenGL Safety Critical 2, which is an open standard from Kronos. We have added support for model-based design tools, an open source tool from ESA, which is called TASTE, and also support MATLAB and Simulink. And we have also a digital twin for the same platform, compliant with industry standards. Here you can see the architecture of our integrated platform. We have 8 partitions that comprise our 3 use cases that run in parallel. We have a data replayer from OHB that provides the data from the Nmap satellite, and this is connected to a test EGSC for telemetry, display, and sending of telecommands. Here you can see our lab setup, which was at OHB premises. This is where all the magic happens. This is our FPGA that implements our SoC, and this is connected to a computer that provides the telemetry and telecommands, and as well the data from Nmap. And we have also UARTs that emulate the devices that we control. So this is the integrated prototype, how it looks like. We have a lot of technologies. We have Ethernet. We have UARTs. We have the hypervisor with time and space partitioning. We have a novel functionality that allows one partition to control the access of another partition. We can share the Ethernet and the GPU between the partitions. We have the replaying software from OHB, and as I mentioned, this uses real data from the Nmap satellite. We are using 21 temperatures from the platform. OHB created a telecommunication software stack and ported their application to RISC-V. This is the support that we added to TASTE. And we have, as I mentioned, support for TensorFlow Micro, so we can use the accelerator and the GPU through a high-level programming interface. And we can use this at bare metal with RTEMs or with the high performance, the hypervisor. Also, the applications can use seamlessly the GPU, so we can have multiple partitions sharing the GPU. The integration was really easy. Each of us integrated the different use cases, and then we provided everything to OHB, and integration was really smooth, demonstrating plug and play functionality. Here you can see our multi-core schedule and our resource schedule. And here you can see that we have been using some of the partitions that were using a lot of resources. So the instrument control case, it's similar to what we have seen before, so I will not go into the details. It was a real OHB use case that was ported to RISC-V. We had the interlocks that were moved to software to reduce the qualification cost. And I will skip very quickly. We had an FDIR use case based on the temperatures, similar to the previous talk. And very quickly, I will talk about the high-performance use cases. We had the cloud screening that was accelerated using our accelerators. We had 3 different versions, one CPU, one using the AI accelerator, and one about the GPU. And we achieved 2x performance using our own accelerator. For the GPU, the performance was not that high because of the small configuration that we have used, but in the future, we think that we can reach the performance levels that we can achieve with code GPUs. And similar results we achieved with the SIP detection, higher performance, 2.5 times this time, and for the GPU, we had a similar performance. We were also able to share the GPU and the AI accelerator from different partitions. So we have performance numbers also for that. You can check my slides. And to conclude, we have built a RISC-V platform with qualifiable software stack that can be used in institutional missions. We had several use cases that were deployed on the same platform. We achieved significant acceleration and also great savings both at hardware and software qualification. And with that, I conclude, and I will be happy to answer your questions. Here you can see where everything will be available as open source, and we will also contribute our code to OBP Mark at ESA. Thank you.
Thank you.